Find the maximum rate of increase in the function f of xy equals e to the xy at the point 1, 1, and find the maximum rate of decrease of the function f of xy equals y squared over x at the point 3, 6. So the rate of increase or decrease is going to be given by a directional derivative. And the directional derivative is the gradient dotted with the direction vector. And the dot product is the magnitude of the gradient times the magnitude of u times the cosine of the angle theta. And this is just this because the magnitude of u is 1. U is a unit vector. So this is maximized when the cosine of theta is maximized, and that happens when theta equals 0, because then the cosine of theta is 1, and it's minimized when theta is equal to pi, because the cosine of pi is negative 1. And if the theta is the angle between u and the gradient, so if theta is 0, then that means that u is in the same direction as the gradient. So to find the maximum rate of increase, we want u to be in the direction of the gradient of f. And then to find the maximum rate of decrease, we want theta to be pi, which means that u is in the opposite direction of the gradient. So u is in the opposite direction of the gradient of f. Okay, so we have to find the gradient of each function, and then the vector u in the first case will simply be the unit vector in the direction of the gradient, and the vector u in the second case will be the negative of the unit vector in the direction of the gradient, and then we will calculate the directional derivative, and that will be our maximum rate of increase or decrease. So let's calculate our gradients. In the first example, the gradient of f, which is the vector f sub x comma f sub y, the derivative of e to the xy, e to the power xy, is chain rule e to the xy times the derivative of xy with respect to x. And here it's e to the xy times the derivative of xy with respect to y. And then we want the gradient at the point 1, 1. So we put x equal to 1 and y equal to 1. And that just gives us e comma e. And that is not a unit vector. So u will be a unit vector in the direction of this one. So that's going to be e over the square root of 2e, and then e over the square root of 2e. In other words, it's 1 over root 2, comma 1 over root 2. That should be a unit vector. If you square this, you get a half. Square that, you get a half. Add them, you get 1. So there it is. There's our unit vector. So then the maximum rate of increase in the function is in this direction. So the maximum rate of increase will be the directional derivative in the direction of this vector of our function, which is our gradient at the point 1, 1. We should probably put that in our notation here. And that's going to be the gradient at the point 1, 1 dotted with the vector u. And that's e dotted with 1 over root 2, comma 1 over root 2. So you multiply these together and then add. So this one is e over root 2 plus e over root 2, which makes 2e over root 2. And 2 over root 2 is root 2. So this is root 2 times e is the maximum rate of increase in this function at this point. Okay, so now we do the same basic thing to find the maximum rate of decrease, except instead of using u is the unit vector in the direction of the gradient, we will take u to be the unit vector in the opposite direction of the gradient. So we will just insert some minus signs to flip the direction of the vector. So let's first find the gradient of f. So we need f sub x and we need f sub y. F sub x, the derivative of 1 over x with respect, is negative 1 over x squared. So here the derivative with respect to x, the y squared is a constant, so we get negative y squared over x squared. And then the derivative with respect to y, we have y squared over x. The x is a constant, so it's just 2y over x. So there's our gradient, and then we need the gradient at the given point, which is 3, 6. So x is 3, so we have 9 on the bottom, and y is 6, so we have negative 36 on the top and 9 on the bottom, so that gives us negative 4. And then 2y over x, it looks like that's going to be 24 divided by 3 is 8. So there's our gradient. Now we want u to be the unit vector in the opposite direction of this vector. So this vector, the gradient, has a magnitude of the square root of negative 4 squared plus 8 squared, and that's the square root of 16 plus 64, that's 80, and that's 4 times the square root of 5. So that's the magnitude of our gradient. So to make a unit vector, we will divide both components of the gradient by its magnitude, and then we want the opposite direction, so we'll put a minus in each component as well. So we'll get a positive, and we'll get 4 over 4 root 5 and negative 8 over 4 root 5. And of course we can simplify this ever so slightly because 4's cancel, and we get 1 over root 5 and negative 2 over root 5. So that should be a unit vector. We should just double check that because we did some arithmetic here and we could have made a mistake, and the arithmetic here is pretty easy. If we square this, we get 1/5. If we square this, we get 4/5, and then adding those will give us 1. So this is a unit vector indeed. And so the direction, the maximum rate of decrease is in this direction. So we want the directional derivative of our function at the point 3, 6, where our gradient is this vector and u is this vector. So we just have to dot them together because the directional derivative is here. It's the gradient dotted with the unit vector. So our gradient is negative 4, 8, and our unit vector is 1 over root 5, negative 2 over root 5. Multiply these, we get negative 4 over root 5, and here we get minus 16 over root 5, so negative 20 over root 5, and 20 is 4 times 5, and 5 over root 5 is root 5, so negative 4 root 5 is the maximum rate of decrease. The negative is telling you that the function was decreasing.